Today we have Alex. Who's going to give her talk, Invisible Castles and Interdisciplinary Structural Engineering. I'm going to introduce Alex really fast to you. I know it's a little bit redundant because you don't know who she is, but do you know that she's currently in her second year of Masters of Applied Science, Structural and Earthquake Engineering degree, specializing in massive timber. But before that, she spent a year in Masters of Architecture program at UBC School of Architecture. But before that, she was in the bachelor's programs, and she holds a Bachelor of Science in Civil Engineering and a Bachelor of Art in Painting from University of Colorado. There she is.
Thank you. This will be pretty casual because it's practice for a later talk I give to my structures team, and that's practice for a talk I did with the structures seminar, which is everyone in the engineering department, which itself is practice for a talk I give to the American Society of Civil Engineering conference in April. So this is going to be pretty casual, and please let me know if I mess up because then I can fix it. Okay, so I'm talking about what I'm doing here basically, and I thought about asking that because I've had a lot of people ask me, well, what do I do? And I tell them I'm a structural engineer. And they say, ooh, well, first they say, ooh, that sounds fun, which is not a word I would choose. And the second thing I usually get asked is, what is a structural engineer? And I've mostly been saying, you know, I'll get back to that. Mostly I've been saying I make sure buildings stay up. And oftentimes they'll say, is that like architecture? And I'm like, well, really used to be the same thing. And it probably hasn't been the same profession since about this guy. This is Gaudi in Spain, and he was an architect, but he also played around with manicular forms and would drape cloth from the ceiling, and whatever form that made was the exact opposite of what he needed. And so, in effect, he was playing around with shells, but anyhow, he did crazy stuff like that. Nowadays, architecture is more going to be something like this. This is the Seattle Public Library, which I recommend you go see if you're ever in Seattle. It's pretty close. It's crazy. But the engineering part of it, which is very important, is shown here pretty well. This shows the actual skeleton of the building, and you can see all the cross braces in there because Seattle, like Vancouver, is in a seismic zone, and it's probably a good idea not to have that fall down while you're trying to read a book. Although I imagine like the different masses in there must have been fun to play with. So again, I say usually try to make sure buildings don't fall down, but that's not actually what I do. I may or may not have written that. I actually design buildings to fall down, but at a very certain point. This is a professor of ours. He asked us to point out the weakest points in the structure, and we all pointed at the red circles, and he's like, good job, you're either a terrorist or a structural engineer. Because you have to design the building to be weak at certain locations. And the reason why we do that, especially in the seismic zone, is because when the earthquake comes, that's quite a bit of force hitting so much mass. Or it's a lot of mass moving, so it's a lot of force. And you want the building to just move just enough that it won't kill everyone, but not so much that it, falls over. Because if it's too rigid, it crushes people, and if it's not rigid enough, it just kind of flops. But anyway, moving on. When I was an undergrad, this is what I thought engineering was, which is a lot of equations trying to describe what's going on with a force. I kind of missed that because I could see it. Nowadays, I do more of this stuff, which is a lot of clicking on a screen and trying to make certain lines look like other lines at this point and produce different numbers. And it's really odd to me because it's coming across now more as an art project in this sense. It's more visual. You're not yourself doing a lot of number work. You missed that. But again, I can tell you, I have an arts degree. So this is my senior arts painting series. I did a lot of these. And then it's the idea of attributing engineering concepts to art is itself not new. This is a famous picture. It's called Garden of Earthly Delights. It's by a painter named Hieronymus Bosch. And most people who look at this go, ooh, what the hell is going on here? And it's usually interpreted as Adam and Eve in the Garden of Eden, and I don't know how to say this, prehistoric man frolicking around and committing all kinds of sins. The next panel shows hell, which is also just crazy. But if you look into Hieronymus Bosch's background, he was also hydraulic engineer. He designed fountains. He was also an alchemist. And if you read into it enough, you'll see that all these little symbols are referencing alchemical processes. The circular pattern represents changing the chemicals. There's a lot of references to chemical change and interacting compounds. Then when I left architecture, I had a brief semester of going, what am I doing with my life? So I took engineering and art classes again. And I had to study for my advanced concrete design final. And I thought, oh, I have to do an art project for my final. Also, I might as well kill two birds with one stone. And so I did a fake concrete column out of boxes. And I did all the design calculations on the outside. And the calculations are there to work out punching shear, where the floor plate itself is too weak and it collapses or breaks around the column. The floor drops, it hits the floor below it, that causes another drop and your whole structure collapses. And so that is what that is right there. All the rebar is made out of Twizzlers. And I made sure to put little comments in there where the calculation went wrong, just so it would convey the fact that, yes, engineers do panic and think, but it's not just strict numbers. And so when people ask what exactly I do, I say I'm a timber engineer. And usually when people think of timber engineering, they think of light frame housing, which is what most timber structures are in North America. It's these are all these little stick series, they're 2x4s, 2x6s, sometimes 2x10s. You may or may not have an engineered wood product in there, but they're going to be about this size, and I'll get to why they're only that size in a bit, but this is usually what people think of. This is not what I do. There's also heavy frame, which is a good example. It's when you start to get a lot of Game of Thrones type sort of buildings. Green College itself is an example of heavy frame. That's when you're starting to get wood sections that are about up to 2 feet by 2 feet, say. They get pretty massive. But that's hard to do nowadays because it's hard to find trees of that quality that big. So usually you do see more light frame because it's easy to get little pieces like that. And you're seeing less and less of this because it is tougher to get sections that big. And usually people, when they do build like this, they want timber frame joinery, which is old-fashioned, it requires a lot of skill, and it takes a while, basically. So what I do is, I should mention this. This is also a heavy frame structure. It is also the tallest wooden structure in British Columbia. You may or may not have been to it. That's where Steamworks Brewery is. It is 9 stories tall, and that is all timber with steel connections. That's important. I'll get back to that. This is mass timber. This is what I'm studying. All these curved arched ribs are going to be out of glue lam, or nope, looks more like laminated veneer lumber. But you can shape them into interesting forms and carry huge amounts of load. And eventually, this might have been here, this is in the Earth Sciences building. That structure is timber members with steel connections, and it has a really nice back to it. It's starting to look more and more like a steel structure in its basic form. You have large members, and you've got cross-bracing for seismic loads. And another good example is the Richmond Olympic Oval, which you may or may not have been to. I recommend going there because it is a very pretty structure. That's a 100-meter span. That is also a hybrid structure of timber and steel. And so what I'm doing is studying 3 different hybrid timber high-rises. They range from 30 stories to 40 stories. What I've got to do is take what the architects have proposed. These are all proposed by architects. And put them into a structural analysis program, see what kind of loads come out of it, and compare how much it costs to build them. Most of them rely on prefabrication, where you have the wall facades already assembled, you have your beams and columns more or less put together, and on-site you just screw them in together. And so compared to, say, a purely concrete structure, a mass timber high-rise will take about a day per floor. A concrete structure will take longer because you have to let the concrete set every time. And so this is the closest we have to it. This is the Life Cycle Tower. It's in Austria. This one's 8 stories, but they think it can go to 30. Well, I'll see if that's possible or not. Probably is. The real reason why we haven't built any structures this tall is because, again, most people think of timber as light frame. It can be it's often more expensive because concrete is just easier to get, steel is just easier to get. And there's not a lot of design guidelines because mass timber is unconventional. All the connections you can get to use in that system are unconventional through proprietary means, which means there aren't standard design guidelines on how to use them. And building codes are also a massive problem, and that's not without good reason. Mostly it's because of fire, which is understandable. This is the San Francisco fire that resulted from the earthquake of 1906. All the timber structures, well, not all the timber structures, but you had a good, I want to say 80% of the city burned down. And so, of course, after that, all their codes changed. They said you can only build timber structures up to 3 stories. They didn't want this to happen again. Everything that's not there used to be there, if that makes sense. There were a number of fires. This is the one in Chicago in 1870s or so. But it's important to note that the cities that were there then are not the cities that we have now. This is what San Francisco looked like at the time. Your sidewalks were all made out of wood product. A lot of your transportation was horse-based, which meant you had barns in the city, which meant you had hay all over the place, which meant you had kerosene lamps lighting up your barns. You had, this is what your fire truck looked like. It is made of wood. It didn't have a lot of power to it, so you had to park very close to the fire, which meant it also started on fire quite frequently. You didn't have communication between fire trucks, so in the Chicago fire, they told them where to go. It was the wrong place, and so they had another half hour to get around. So we don't have that. We have this, which is much better. But even then, that kind of hose power, that's not going to get up to your upper stories, and a 30-story, 40-story structure. So we can't rely on that necessarily. Most of the fires started off in warehouses or barns again. There's no fire protection. It just wants to burn, basically, looking like that. Nowadays we put fire retardant spray on most things, which helps. You can also put gypsum on the walls, which also counts as fire barrier. And you also have drop ceilings themselves, which also provide a fire barrier. And of course we also have sprinklers. You can just see them in that structure there. Sprinklers are very important. I'll get to that in a second. But can we rely on these systems? Well, you can use fire spray on, but you don't necessarily have even coating all the way through, which means that your fire can still get in. It's not reliable. Sometimes over time the spray just falls off anyway. We're in a seismic zone, so of course when you go through an earthquake, this is what happens to your gypsum wall bar. It just cracks, so that's not going to provide enough fire protection. And then of course sometimes your clients are just the most helpful people and they just remove it themselves because they think it looks cool. So that's a problem. So you can't actually depend on these systems for your sole fire protection. At some point you have to rely on the members themselves. This is a diagram showing how wooden sections burn. And it's important to note that in this diagram that the outer section of course is burned away. You can see the charred area. The residual section is what is left, and that still has the same capacity as a normal piece of wood, as the normal member. And so what you do is you oversize these to provide you a little more extra time so that as the section burns in, you still have a residual member to provide support. And so here's a nice little detail showing a wooden section that's been gone through a fire test. And the interesting thing here too is that when the fire burns through, it's that temperature at that surface. It's not that temperature on the inside. It doesn't spread through like steel, which for some reason building codes think that steel structures don't have a problem with fire. I don't know why it's a steel concept. But of course, ideally it'd be nice if the building just didn't move so much in the first place. We could do that. And so you can do that in several ways. This is a tuned mass damper, and this is a famous one in Taipei 101 in Taiwan. You put these in seismic areas, and what this is a counterweight located usually at the top of the building, but in other places too. And so when your building moves, this weight goes the other way and keeps it from moving as much. There's some terrifying videos on YouTube of how these things in action. There were screams. It's great. I thought, well, there's different kinds of tuned mass dampers. This is a liquid tuned mass damper. I said, oh, what if we had that as a counterweight, and that would supply the sprinkler system? Because of course in an earthquake, which Vancouver has, and which caused the 1906 fires in San Francisco, your civil infrastructure kind of breaks down. Your fire trucks can't get through rubble. Your water systems might break. You have to rely on an in-house water system. And so it looks a little bit like this. If this doesn't scare you, I don't know what is. well, this is kind of how we model how a building operates in an earthquake. It's balls and sticks. We get more advanced than that, but this is the basic concept. I want to put in multiple tube liquid column dampers, which sounds really fancy, but what essentially these are U-shaped pipes with water in them, and you calibrate them to a certain frequency. And this way you can have several frequencies in the same building so that you can make sure that they don't overall actually contribute to the sway instead of dampening it. And you can locate them at different points in the building to optimize that. So my project is to take the proposed high-rise structures and put these at half points or third points in the structure, see how much that extra load causes the connection design cost to go up, and then compare it that way. Because the main thing we were told, at least in my department, is that the reason why we aren't building these is because it just costs too much. It costs maybe 3% more, maybe 5% more, but the contractor, the developer, won't do it because it just costs too much. But then again, you do get fancy structures like the Seattle Public Library. That wasn't cheap. And so my feeling is that, well, if we can get architects to start specifying this and selling it, that we'll see more of these kind of structures. So I say it's more of a cost versus attraction kind of balance. Well, I'll be darned if architects don't use straight lines. This is a particularly cool thing, but holy crap. So, well, how can you take this and put it into SAP? SAP doesn't like curves so much. You can kind of get curves out of it, but it really prefers things to be orthogonal. Well, how do we do this? Well, I thought, well, I'm going to have to look at what the architects use. Can we do this in timber? Well, some architects are trying. This is a timber shell dome structure. It's made out of plywood, but it's a good start. They have something larger. This is also, they're all in Germany. This is the interior of it. It's a decently sized thing. This is also, this is in Spain. This was a pavilion. They called it the mushroom. I think it's cool. But so what are architects using to make all these fancy lines? Well, they're using a program called Rhino with a plug-in program, part of it called Grasshopper. And it looks, that's a little mock-up of the Beijing water cube. They probably use Rhino for that because, again, it's all these strange shapes. But that's how they generate these forms. It's a very neat program. This is a program I picked up in architecture, and you use genetic algorithms, which is a fancy way for saying a mathematical function that builds a shape. It's very versatile. You can make it hook up with other programs. It depends on little plugins you can download online. You stick into Grasshopper, which are all free, but you just have to know how to use them. They can do geometric simulations, they can do environmental simulations, they can figure out how much energy you're using, they can simulate daylight, they can simulate wind. They have optimization plugins, so you can tune which parts of the functions you want to encourage and which ones you don't. You can communicate with Excel, and you can also have a software interaction with other kinds of software, which is important, because then we can hook our architecture program up with structural analysis programs that we've been using. I say ETABS is sort of there because I have the plugin for ETABS, but every time I open it, it crashes. I don't think that really counts. What you need to make this work, you need a crazy powerful computer and a large amount of coffee. It takes a lot. You can find a lot of examples online, but some they usually look like this. And so you spend a good deal of time just trying to figure out where everything is going, because whoever made it knew what they were doing at the time, but you're like, I don't know. Spaghetti code. Whoa. But this is what I eventually want to do. This is an example of video that Thornton Tomasetti, it's an engineering firm, did. They now use this kind of software interaction to design all their structures. And this is how they designed the El Manal Stadium in Iraq. Let me see if it needs to go. Or maybe not. Oh, there we go. All your geometry is in Rhino. And that's hooked up to Grasshopper, where it optimizes things. And that's fed into SAP, which figures out all the loads and returns it back to Grasshopper, which then calibrates everything again in response and does iterations. And this is how they figure out the best forms for them, according to either cost or load demands. This is for deflection. first time I saw that, I was like, oh my god, that'll save me so much time. Anyway. So that's one side of things. I am actually working with the architects currently. They want to build shells out of CLT panel, and I'll get into what CLT panel is, but basically want to design those timber shell structures I showed earlier, but on an actual massive scale, like swimming pool size, stadium, that kind of thing. So that's interesting, and this is what a folded plate structure is. Usually these are concrete. You can see what this looks like here. Again, folded, they're not taking concrete and folding it, so, but it's a fold. There's also double curved shells, which look nice, and they rely on, and again, I get to do the current protection design for this. And so it's a bit tricky because you have to look at the material. Like, well, what are we working with? We're working with cross-laminated timber, which is what all the floors in the Earth Sciences building are made out of. And what these are your 2x sections, and they're put in little stacks, and these are layered in alternating orientations, and they are glued the hell out of each other, and that's it. That's what that is. It's a solid, huge piece of timber. Like, you can't grow trees that are 3 meters by 12 meters and rely on that. This is what they can go up to 3 meters by 12 meters, solid timber. They can be up to about 40 centimeters thick. It's heavy stuff. It's nice in that it has strength in both directions, and that's important because it's timber. I like to describe it as a bundle of straws. You can press down on the ends of the straws and it's fairly strong, but if you go through the middle, they just kind of crunch. And that's because it kind of is straws instead of timber. So when you have a section like this, you've got timber running in both directions, you've got strength in both directions. But you might notice that there's not, well, that picture shows it, but there's not actually the same number of layers in each direction. So when you do calculate the strength of that panel, it gets a little complex, depending on which way the load is coming from. And the tricky thing is that the architects won't give me a shape. I don't know about you, but the basic way that engineering works is that you get a shape of some kind with dimensions from the architects, and then you figure out how much, you have an idea of how much snow is going to sit on that, and then you divide up the area into little tributary areas, and you say, okay, that much load is going onto that member, and but you have to have dimensions. Like, there's no dimensions. That's really hard. So I thought, well, I have general ideas of what the connections will look like from plate to plate and so forth, but it gets tricky. But we'll get back to that later. We also want to do double curvature, just like concrete, which is nuts because no one does that. They couldn't figure out for a while. They were banging their heads against the wall, and I said, look, let's look at a barrel. A barrel has double curvature, and we'll just make really huge barrels. So what they do is, to make a barrel, you take your 2x and you curve the edges so that when you do bend it into place, it has a curve this way and a curve the other way, and different curvatures. So they are trying that. They're making a double curvature CLT plate with the alternating orientations, and this is the mold formwork for it. And that is as far as it has gotten, because they haven't gotten their stuff together since then. But we're getting there. But on my end, I want to make sure I'm designing this right. I want to know what the shell forces are, because shell forces are tricky. Well, there is a nice book about this called Shell Structures for Architecture. But I read through that, and all the chapters written by the engineers were essentially, whoa, this stuff is crazy. Maybe it's right. We're not really sure. Sometimes we just go, yeah, this is most of them were just saying, this is really complicated stuff. Yeah. I'm like, okay, it's great. That's great. So what I thought about, okay, when you design the panel as a floor panel, it is a shell, the whole thing is a shell, but the design procedure assumes it to be a beam. So I said, okay, we'll just assume that these are beams and design for the weakest direction and go from there, and that should be a good assumption. So I've been sticking these things through Rhino and Grasshopper into SAP, and I get a line, yay! So this is coming along. It's tricky because SAP likes concrete and steel, and I'm not using concrete and steel, but we're working on that. The double curvature plate. Can we actually get plate action out of that? Well, that's coming along. I do get deflections out of this now, so that's exciting. This only took 3-4 months to figure out, which is a little weird coming from an arts background, because I'm like, if I actually just wanted to make a picture like that, you would just sit down for 2 hours and just draw it. Instead, you go into engineering and you spend 4 months to make the same thing. It means more, but a little odd. Then I started applying this to my thesis and comparing the structures. And so I said, well, you know, it'd be nice if we could just push buttons and make the structure taller or change the size of things. So this lets me do that. And in the meantime, I'm still puzzling over the shell structure because, again, we don't have a shape. Which means that I don't know which way the panels are going to go. They might load it in the preferable direction, but they might try to squish things and make weird shapes. And so I said, well, I guess I have to make something that's parametric so that when we do have a shape, we just put numbers into it and it spits out a form that says this is safe. So I've had to learn Python and develop my own components for Grasshopper. And then when it comes to the connections in between them, it's like, well, yeah, we've been doing a lot of screws. I prefer self-tapping screws because people make those, but my architects want to use entirely wooden structures, which is a little aggravating. But I said, well, okay, we'll use finger joints, just like in furniture. It'll look like kind of like this in the CLT plate. We'll cut off the edges, but that shows it pretty well. And it's hard to make that with all those weird angles. You have to be, especially with timber engineering, you have to be exact, very, very precise. So we're going to use robots to cut them. We're getting access to that. So you have to go back into the Grasshopper code and develop components that take your geometry and translate it into G code for the robot to understand. That is a 5-axis robot. That's very expensive. And eventually I want to be able to make CLT panels with this kind of connection and bond it with adhesive, because the adhesive itself is actually stronger than the wood. This way I can get a moment connection so I can do this, but bigger. And in the meantime, after that, I would like to see CLT panels applied to structures which are much, much larger, different orientations. And I'm sorry, I don't have any Batman drawings for you today.